So from the Euclidean spaces, there are other examples, and the space of functions, we derive the idea of a metric space, and we define it through those three axioms. And now what was done at the end, we are moving towards topology, which is even more abstract, because we do not, we're not going to rely on distances anymore. So the concepts will be still, all topological concepts will be there. It is open sets, closed sets, limits limits of sequences and functions, as well as continuity of functions. Okay, so all right, so that's where we are. This is what we're talking about. The definition of open set in a metric space is right there at the top. Okay, so this is. So I put it in Rn, but it actually works just fine in any metric space XD. Okay, so if we can speak of distances, we can certainly think Rn, or we can think any metric space. Okay, so but the examples is where everything really just the theorems are good, but examples are really if you have enough examples, your life is much easier. So those complex concepts are become more tangible, and then you think of all the examples and counterexamples for every theorem that you encounter. So that's examples of open sets in R and R2. So in R1, as you can see, these are intervals, and in the meantime, open intervals, that is, infinite or finite. Okay, see right there. And then there are closed. Well, first of all, how do you define closed sets? Right here, they're simply they define it actually in two ways, as you can see, 1 and 2. And one definition is metric. So say once again XD. Since in a metric space we understand convergence of sequences, right? Then we can understand such a thing as a closed set is defined through this special set, which is explain the word closed. Is that every convergent sequence converges to one of the points of the set. Okay. In the meantime, the alternative definition relies on the concept of open sets, and you just say it's a complement. Okay. The complement of an open set is called closed. Okay. So then, for examples, we go to Euclidean spaces first. And as you can see, the intervals is number 1, closed intervals. The words that were used in calculus and before is open intervals, closed intervals, and now it is in one place, and also fits into the narrative of the metric space. So, but these are the examples: finite or infinite. Once again, that's what we faced at the very end last time. Is the question is. Open, neither open nor closed. An interval that is neither open nor closed is called, or doesn't matter what it's called. What is it? Open, closed. What's left? What are their intervals? Do you know? Other than infinite. 0, 1. There are 2 more.
Open and close and close and open?
Right. The ends are included or not included. So neither. Okay. So it is. Not every set is open, not every set is closed, not every set is open or closed. And it is, if you pick at random, it will be obviously neither. So there they do carry some information about them. Okay, so then examples of open closed set in the metric spaces will be also, in high dimensions, you can think about it as once again open disks, closed disks, sequence combined with its limit. Another example of a closed set. As the example I showed you here. Okay, sequence is itself is not closed if it is convergent to a point elsewhere. So once again, 1, 1/2, 1/3, 1/n, not closed or open for that matter. But if you add 0 to it, and it is closed. Okay, so this is another example. And in fact, what if let's see if we understand this. Well, how about this sequence? -1 to the n plus. Oh, let me put it this way. 1 plus 1 over n, -1 to the n. Okay, so let's, you see what this sequence does. What does it look like? It oscillates between -1 to the n. It gives oscillation between positive and negative, but also the magnitude changes, right? So in the up down, but the size changes. Okay, so the sequence then, I'm not plotting the sequence yet. I'm plotting the sequence as a sequence, not as a set. So I have n's here and say y's here. So an is this. So if I plot this, I'm going to have something like this. So it's going to be so if it's 1, then it is 2 or something like that. So maybe 2, and then it goes up and down like this, and then yeah, something like this. So as you can see, it is getting closer and closer to the line. So this is 1 and this is -1. Okay, and so the sequence is getting. You see what's happening. If you look at these two sequences separately, you shouldn't, but suppose then they're what are they doing? They're approaching respectively 1 and -1, right? So this is say 0, 1. Well, it's not a 0. Okay, this is 1. This is 2, 3, 4, 5, 6. Okay. All right. So that is not a set. This is a sequence. But as in comparison to what I have here, I think of these as sets, not as sequences. Remember, sequence is a function with just integer inputs. But if you want to think of it as a set, then you have to look at the codomain. Okay, so in this particular case, I will be looking at the y-axis only if I want to see a set, the sequence as a set. So this is sequence as a function, and this is as a set. Okay, so I'll just what do? I just push them all to the x-axis, to the y-axis, and see what they look like. This is what it looks like. This is 0. Once again, let's say this is 1 and this is -1, and my values will be behaving like this. Well, they will be alternating between the two, between positive and negative, but otherwise they will look like this, right? And here, like this. Okay? So as if there are two separate sequences. That is, so we're looking at our sequence as a set. I mean, the sequence is not a set, but you can make a set from a sequence, so like this, an. So this is a set. This one is a set, while this is a sequence.
As you go to the y-axis, wouldn't it like oscillate between -infinity and infinity? Like it would get really tall right there?
No, 1 over n. I'm adding 1 over n. So the swing is diminishing. The formula, you see the formula for 1 plus 1 over n. So it will be 1, and then a little piece, which is 1 over n, will be getting smaller and smaller and smaller.
But as you're going to 0, that would get smaller.
No, what is going to 0?
Like if you're going like from the right, to n's going to 0.
No, n goes to n goes to infinity, right? So these are the n's. They go to infinity.
Right, but before it gets to 1, isn't there a section where it's going like -infinity to infinity?
Well, if n is equal to 0. If n is equal to 0, or close to 0.
Yeah.
So you're referring to, I think what you're referring to is a function rather than a sequence. So if I take roughly the same formula and I take, say, y equal 1 plus 1 over x, then its graph will be, like this, right? So indeed it has infinity on two ends, here and there. Okay, but the sequence does not. It has only one infinity to think about, because there is a starting point there, and because of the only one element there, say n is equal to 1, so you have to be specific here, n is equal to 1, so you don't divide literally by 0, then no, these are the only values, right? So 1, n is equal to 1, 2, 3, 4, and then the only possibility is to anything interesting happening is at the end, at the other end, and at infinity.
So the main of the sequence is only the integers.
Right, not typically both infinities, but there's a starting, it's like array, but it cannot have real values other than, so they have to be integer valued, yeah. Typically you don't even skip, you go one by one. The beginning point is usually arbitrary pretty much. Okay, so I didn't make the right picture here, so this is not quite. Okay, let me start over. So this is my y-axis. There are two potential limits, let's say, and then I'm going roughly without taking a lot of care of what's going on exactly. These are some of the elements of the sequence, so as you can see, it is a subset of the y-axis. It's like the image of the sequence of this function. Okay, so just projecting everything on the y-axis from the graph. So this is the graph. So as a function, meaning the graph. Okay, and this is like the image. Same thing, but once the image is a set, while a function is given by its graph. So that's the point of this picture. So if we now look at this set, so the right picture applies. If we look at this set and we ask ourselves, is it closed? This one, the blue numbers, is it closed? Why not? It is approaching the sequence. There is a sequence in that set that is approaching 1. So let's call it M, whatever. So this is my set M. There is a sequence that approaches 1, and yet 1 does not belong to it. Okay, so 1 plus 1 over n goes with positive ones, so 2, 4, 6. It's a sequence, and the sequence converges to 1, and yet 1 doesn't belong to it, so it's not closed. So no, to make it closed, what do we do with it? How do we make it closed? Add 1 to the set. But it's still not closed because -1, same story. So in other words, say n is equal to an, that sequence that we already have, union of -1, 1. This one is closed. Okay, so, well, there you go. Okay, so any questions about this example? So most of the complexity might appear, might be seen at the more basic level. The challenges of these concepts appear in dimension 1. So that's you can see already closed versus open is here for us to face. Okay, so closed set is two way to define it. And so when you ever do that, you have to demonstrate that it is indeed these two definitions are equivalent, like that. Okay, so which means that you have an if and only if theorem. And I did, so well, that this one is the rest of this page is about Green's theorem and justification for the idea of boundary. But the theorem that, I thought I started proving this theorem. or it is maybe slightly elsewhere. So I want to demonstrate that these two definitions are equivalent, and well, I guess I only looked at the picture over there to come up with the idea why this is the case, and there is some argument here on the right of how we would approach it. So once again, then open sets are defined through balls. So with the picture like that in the metric space, and then you can use balls once again to define limits, and then you can define closed sets. Or you just go from open sets, you go straight to closed sets through as complements. Okay, so that's certainly not the same thing. We can prove it that it is indeed the case. Then we can go both ways. Okay, so the argument is here on the right. Roughly, if it's incomplete, we certainly can talk about. Okay, I asked you to finish the proof. Okay, now I remember. Okay, so this is the outline of which way does it go. Suppose it's so open. So this part is the proof going which way from this way. Okay, this way. So from the first definition to the second. So you suppose that this set is open in this. The set is closed in the set of the. No, it's actually the other way. Sorry about that. It goes the other way. So we assume that it is closed in the sense of the second definition. So assume it's the complement of an open set. Okay, and then we proceed, as you can see, open complement of an open set, and then by definition we go to look at the definition, then applying next definition, which is definition open set, and that's what you see here. Okay, so all right, so then as you can see, the definition of an open set is. The definition of an open set is here, followed by how we apply the definition, which was applied to the complement of G, but then it is now translated into the statement about G. So as you can see, there is a ball around X, which is so if X does not belong to G. Okay, so let me put it this way. So what we have demonstrated is X does not belong to G, then for some R positive, the ball around it also does not touch G. Okay, so that picture on the right. So X, as you can see, does not belong to G. And then, which means I don't want to use V again, so it means that there's a ball around it, BXR, right here, that does not intersect G. Okay, so we supposed to, from this, we're supposed to conclude what? That if there is a sequence convergent to A, then A belongs to G. Okay. Insert some space here. Okay, so how do we demonstrate that? So once again, we have established this. So this is what we know about the G, okay, from the second definition, okay, and then what we supposed to demonstrate is the first definition. So from this, we somehow have to derive the second definition. So what do we do? How How would we prove the first definition from that statement in the brackets? Now look careful. Take a careful look at the definition, number one. So well, how would you prove that we just did it when we looked at that example a minute ago? We did prove that that set was closed. Okay, so and that's what we need to do, just in a more abstract setting. So how do you prove that a set is closed based on the first definition? How do you do it? Well, you start with a sequence, right? So a sequence, and for every sequence, a certain condition is satisfied. So, well, that's how the proof goes. So you just say, well, suppose we have a sequence, a convergent sequence.
It doesn't
Yeah.
satisfy the limit condition.
Well, it's supposed to satisfy the limit condition. So suppose there's a sequence and it's convergent. And then yeah, you could go contradiction if you want to, right? So then you can suppose A does not belong. Well, it seems to be a good idea. Why? Because of what the tool we're going to be using is what's in the box, and so the fact that A might not belong to G is a good thing for us because it fits into our plan. Okay, so let me try to write that up. So 1 and 2, we're proving 1 from 2. So suppose we have a sequence AN that is in G, okay? And then AN converges to A, but A does not belong to G, which would make it not closed. So we're going back, we're doing proof by contradiction, right? Okay, so by this, what do we conclude? A does not belong to G, so what do we have about, what do we know about A? A does not belong to G, so then the conclusion of what's in the box is applies. So what is it?
There does not exist a ball around A.
No, there is, according to that statement on the right, there is, for some r greater than 0. So that means there is an r positive, so that the ball radius r around x does not touch G.
This is outside.
Right. So we have then BAR intersection with G is empty for some positive r. Okay, and then we're supposed to find the contradiction between these two. Well, yeah, these two. So you see how that works out? So well, not this. We have actually three facts here combined together. So let me rather rely on this. Let's compare these two. So that ball BAR does not touch G, but on the other hand, the sequence entirely lies in G. So my conclusion is, what's my conclusion? No, not just yet, not just yet. These two statements that are underlined. What's the conclusion? The sequence lie in G, but that ball does not touch G. What can we say about the sequence versus the ball? I want to take G out of the consideration. So the relation AN on one hand as a set, and BAR, what's the relation? The sequence is just a set. So a set lies in G, and so three sets. G contains that set, and on the other hand does not intersect another set. What can you say about the relation between these two sets that are left?
Their intersection's empty.
Yes, that's right. So the sequence is in the set that does not touch that other set, the third set, which means that there is no way the sequence can touch this ball. Okay, so so as you can see, then this statement is to be contrasted with this. So sequence converges to A, yet there is a ball around A that the sequence doesn't touch. So at this point, you already can say it's a contradiction, or if you want to elaborate, then you say, so AN goes to 0, which means that DAN A goes towards 0. If DAN A goes to 0, let's apply R here. I want to be carefully write out the whole thing here, since we started down that road.
I don't get how that goes to 0.
The AN converges to A. So that is part of the definition, or not the part of the definition, one of the interpretation of the definition. Where is it? Here it is. So it is the definition pretty much. Pretty much the definition of convergence AN to A is that the distance between A and A goes to 0. Okay, so it is a sequence of numbers. Distances are numbers, so this is a numerical sequence. So we are within calculus confines of calculus 2. So let's set everything aside, and let's choose R on the left as measurements of how close we want to get.
R goes to 0?
No, R is fixed. There is an R, see, for some R, which means that we have found it, it's there. So you see where I'm drawing it? Now let's write the definition. Okay, so once again, I want to use the simple definition of convergence of sequence of numbers from calculus 2. So what's the definition of this? DNA goes to 0, so it's just, you can say it's like a BN sequence of numbers. So what does it mean the sequence of numbers converges to 0? No. It is entirely calculus 1 definition. And all definition about limits start with the word. What words? Definition of limits start with the same word. For every epsilon greater than 0. Okay, can you continue on from this?
There exists a delta greater than 0?
Well, not delta, that would be about the function. About the sequence, it is there's an n capital. Such that what?
Would it be epsilon equals the limit of
Not equal. The distance between the limit and the element of the sequence will be less than epsilon. So in this particular case, it will be simply dANA less than epsilon. That's all. So once again, this is a number. So we just, as long as we can make it small, 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 and small, as small as we like. That's what epsilon is. It is how small do we want to make the sequence? Well, and we choose epsilon small and small and smaller, and every time we just push the tail of the sequence far into the future, and the making those elements small and small and smaller, less than epsilon. Okay, for every epsilon, the standard of closeness or standard of accuracy, depending on what we're looking at, imagine you approximating a certain number, and then your boss asks you to approximate a certain number, and then if he does not think that you can just give him a number and then he will buy it, but then he might ask you to, I want this with this accuracy, okay? And then how do you do it? You make enough, find enough decimals in that number to provide the answer. Okay, so for every accuracy that is required of you, you will need more work to do to find more and more decimal points, the digits of the decimal representation of that number that you're looking for. Okay, so that's n capital, how many digits you want to have, and epsilon is the accuracy that you asked of. And then next day the boss asks more accuracy, and you need to do more work and find more digits. That's the sequence on one hand, and that's the meaning of epsilon is at least one interpretation is the accuracy of approximation. So what are being approximated here in this particular case is 0, but we just don't. Certainly nobody needs to approximate 0, but if imagine that it was a pi. Suppose sequence was convergent to pi, and in fact we know what that sequence is. It's just say all the digits. Pi has infinitely many digits, but if you truncate it, you have 3, then 3.1, 3.14, 3.11, whatever that number is. It will be longer and longer, and but you need to know all of them if you might be at some point required to find the accuracy that number with some accuracy. You don't know what that accuracy is going to be, so you have to learn how to meet those requirements, and that's the definition of the limit is there. That's the purpose. That's the meaning of epsilon is the accuracy, and n is how many steps you have to make in order to get there. And so if we are approximating 0 with that sequence, then we get me this how many steps do I have to make in order to get within epsilon from 0. That's how many. We don't know what that number is. You might have to prove that. If you're proving this, you might have to indicate what that number is. Number n is. And so, but we're not doing that because we already know that there is a convergence. So there is for every epsilon there is an n. Okay. So we're not gonna do what you may have done in calculus 1 when you had sequence probably limits of functions, and for every epsilon you found a delta. So proving limits from scratch for a specific function, specific number. Okay, so that is certainly what you did in calculus 1. But when you're doing proofs, you don't really you don't deal with specific functions or specific sequences. You don't need to find don't have to find for a specific epsilon find specific n. No, we already have it. That's the assumption is that there is the convergence to 0 to begin with, and then we have the statement. It's a very short statement, but certainly it is a challenge to actually become so comfortable with it so you can use it whenever necessary. And, well, it is necessary now because even though we reach this point, where is the contradiction? So where is the contradiction? I want to point out where that contradiction should be hiding between this statement and that statement. You see the contradiction here? Well, maybe we need to make one more step, and that is the...
Is
well,
R the same as epsilon? Or like,
say it again?
can R be replaced as epsilon?
Yes, except the other way around. You choose epsilon to be R. So the last statement is we're saying that for every epsilon this is satisfied. Any. So let's pick one that number is already there, lying around, or let's pick epsilon to be equal to R. So if we choose epsilon equal to R, which we're allowed to do because we are doing it for every epsilon, we stated that it is true for every epsilon, so let's choose epsilon equal to R. Then you can see, do you see the contradiction between the two statements underlined by blue? The pictures help, and certainly that picture on the right you might still able to use it, but you know, it's just an explanation. But then you still have to write it up, and it's better to not to rely too heavily on pictures. So it's the same. Epsilon is equal to R. So let me put R here just for convenience. Okay, so on one hand, the sequence does not touch the ball of radius r from A.
So the distance can't be any smaller than the radius if they don't intersect?
That's right. So, right. That is the contradiction. So, on one hand, we're saying that it never reaches the distance of r. That's the first statement. The sequence never reaches the distance from A, R or less. That's what it says, the first statement. The second statement says that the tail of some sequence at some point will be less than R. Well, that's a contradiction. Okay, so that's pretty much not much else to be said. I mean, in fact, there is a lot to be said, and I did, but not much else to write. So you have to, when you see something like that, it's still look at it. We spend like a half hour talking about this, but it is like still half a dozen lines of text. So that's not unusual. So you look at your textbook or elsewhere, and the proofs will be this short, and then you have to look at it for half an hour or more, and fill in the blanks. Those leaps of logic. You have to explain to yourself why it's okay, why they're explain every step that is necessary. So you can try to provide more details than we have actually written. So if we try to write out every word that we have spoken, then it will have more details. But on the other hand, so it helps on one hand, but the trade-off that it becomes so long that you probably will have trouble to actually getting the idea, the main idea of the proof. Okay, and so that's also a bad thing. Which one is better? Probably both. Usually the way it is done, you read the short proof and then you go over it with you yourself or your friend with your friends, and then just explain to each other what the details, because every sentence proceeding from the second sentence to the next will be questionable every time. Okay, and so you have to fix it for yourself, and that different people have different explanations and different standards of. Some people take more to convince than others. Okay, but otherwise, it is the proof is all here. So if you roughly add some slightly more words than the symbols, then this is a complete proof of that statement. So if I want to put it in words, I would say that if G is a complement of an open set, then it contains the limit of every of its convergent sequences. Okay, so if sometimes it's a good idea to write words, theorems in words rather than just with symbols. So it is a complete proof, but as you can see, there is a lot to it just to get through it. Okay, so that's one way. Homework finish for metric spaces, meaning that you would go the other way around. Where is it? The other way around, meaning so from 1 to 2. It takes about as much work. Okay. Okay. The boundary. Okay. So so the main connection to calculus is actually through boundaries. Even though open sets do come up, the boundaries is actually something that you cannot avoid when speaking of such a central thing as the fundamental theorem of calculus and all its multidimensional analogs. Okay, so as you can see here. Okay, so so boundary. I don't remember if there is anything else to be spoken about the boundary, but that picture should be on your mind. That's on the left. So as you can see, there's a set, and then a point is in the boundary. If no matter how small the interval is, the ball around it is you take, it will intersect both the set and its complement. Okay, so there. So then the boundary of the set and its complement is the same thing, which makes sense. If we speak of boundary or border, you know, like you have two countries, and then what's the meaning of the border? The border of the one country is the same as the border of the other country, right? So you cannot have border does not belong to either of the countries. So there you go. Okay, so we had let's see if well, okay, so that's the debt that we had left. The union was I skipped over. So this is once again, this is you can think about this as a metric space or in well, it is in a metric space. It is in a metric space. In a metric space, we have defined open sets. Once again, look at this. This is the definition of an open set at the top. Right here. Let me erase it. And now we have to prove properties of them, and those properties are to begin with, the intersection of two open sets is open. Okay, so writing out the definitions as many times as necessary, which is 3, starting with U open. For every x in U, there is an R such that BXR is in U. Okay, V is also open, so for every x in D, there is an S such that BXS, the ball of radius S around X, is inside of B, which is illustrated here. Well, let me start over here. Okay, maybe like this. Okay, so I wrote, I have two sets, both of them are open. I wrote the definition 2 times, but without trying to. That's often happens. Just using the same, copying the definition is dangerous when you do it twice, because you will be using the same terms, the same letters rather, and you might make yourself assume that you're talking about the same thing, but you're not. Okay, so U and V is like 2 separate steps that you make. One step, you write the definition of openness of U, and then for the second one you use the definition of openness for V, but all the ingredients are different, because the different set, they really at this point have nothing to do with each other. Okay, so that's why I call the point in U and in V different names. The radius also is called, the radius of those balls in these 2 sets also have different names. Okay, so then what I'm talking about here is this is B, this is my X over here, this is BXR, this is Y, and this is BYS. So intentionally make them as little to do with each other as possible. Okay, so so that's all good, but really with that's how you write the proof, but you still have to come up with the idea. What is the idea? What is the idea? We need to prove now that the intersection is also open. So somehow, I'll have to do it next time, but let me write it up. Somehow I got to arrive to the intersection being open. So this is how it's going to be. I have to somehow, for any or every Z in U intersection V, there is, how about a T such that BZT is inside of U intersection V. Okay, so you have to prove, this is what needs to be proven in order to, that statement on the right at the bottom, that is what's proven to demonstrate that U intersection V is open. Okay, so any ideas of how to do it? Well, let me give you a picture. So this is what we're trying to accomplish. This is my Z, and this is BZT. So how do I make this from those 2? Okay, so we'll talk about that tomorrow.